the MO that we had for both these reactors is that they had to be extremely transportable. So that means we can get them on the back of a truck or a train or a shipping container on the back of a ship. We can get these anywhere in the world, helicoptered in if necessary. So we started with that parameter, and that was to allow us to use existing transportation infrastructure. But with that in mind, it had to be very safe, had to have passive cooling mechanisms, and needed very few members of staff to actually operate these things. So just to de-risk our company, we built two what we believe are the best design teams in the world, and we gave them the same MO. So within operating within those size parameters and those safety parameters, go out and design a reactor. So
Okay, hello everyone. I have James from Nano Nuclear, and they're making truck-sized nuclear fission reactors, actually a couple of different kinds. And we're going to discuss where they're going with that, the technology, the development, and find out all about it. Let's dig in with James. So you're making the Zeus and the Auden reactor. Tell us about those reactors.
so the MO that we had for both these reactors is that they had to be extremely transportable. So that means we can get them on the back of a truck or a train or a shipping container on the back of a ship. We can get these anywhere in the world, helicoptered in if necessary. So we started with that parameter, and that was to allow us to use existing transportation infrastructure. But with that in mind, it had to be very safe, had to have passive cooling mechanisms, and needed very few members of staff to actually operate these things. So just to de-risk our company, we built two what we believe are the best design teams in the world, and we gave them the same MO. So within operating within those size parameters and those safety parameters, go out and design a reactor. So the first team based out of California, they got to work on the Zeus reactor, and their solution to the problem was if we remove the whole coolant from the reactor, then the reactor shrinks down in size enormously, and you can remove pumps and you can remove a lot of mechanical equipment, and you just radiate the heat through thermal conduction through a solid core. And then just a normal airflow can remove the heat from the periphery of the reactor. It's pretty much the most simple you could possibly make a reactor.
So this is building upon some more recent work Lockheed and NASA were doing with the Krusty reactor. There's some versions of simplified fission reactors where you just get to minimum criticality, and then there's no chance of meltdown because the most you can do is basically just generate power. And then there's also Westinghouse work to use a lot of heat pumps then to reduce any liquid flow, because you have these solid cores that powders and pipes or that kind of thing to transfer heat through the system. So that has been a trend in terms of the technological focus, but not to the point of implementation. So how does yours factor in with how those other systems are approaching things?
So it's a scale thing, really. So for instance, like solid core isn't a new idea, but for instance, the material science has never really been there to allow for a commercial product to be produced. So you need not exotic materials exactly, but you need to be utilizing materials that don't have a big database of information surrounding them, say, sort of like beryllium oxide, that kind of stuff. But now the material science is sufficiently evolved, it's almost at the point now where we can produce these commercial vessels, and it opens up enormous amounts of possibilities too, because as you say, that if every mechanical component was to break in the reactor at the same time, all that would happen is it would just get hot and it would just radiate that heat, but you would never get the
Meltdown.
yes, exactly. The worst case scenario with a reactor is, say, coolant leak, core overheat, core melt. This way, you just have some heat naturally radiating and passively cooling itself. And so
We
we've
just choose a design parameters where the worst case is not bad. Nothing's leaving the system, and basically you're not quite operating the way you want, but it doesn't get get to the point where if you left it alone, the whole walk away safe concept, that whatever the worst case is, I can walk away. I can come back a long time. It's not like I have 0.1 seconds to hit the purge button or do something like that. Yeah.
Yes, exactly right. So, like, obviously, this enables us to operate the reactor with very few personnel at site, and you could even have a central location that monitors the behavior of dozens of deployed reactors. And maybe there's a mechanic on site or someone for security. But if everything was to go wrong simultaneously, everything was to break, the person overseeing the reactor was to be shot, then it would still not lead to that core melt and that disaster, that kind of scenario where you then have a cleanup operation. You would essentially just come and insert control rods, any way you can do it, and then it would just cool down on its own core.
So the physics of what you've done would be, it doesn't go really bad. It can go slightly off the rails. Because you want to, the NASA and the Lockheed version with that 10 kilowatts or 40 kilowatts, which is a far smaller system, you're looking at 2 megawatts, possibly more. And the large scale reactors that existed for 50 years have generally gone up to 1 gigawatt, 1.5 gigawatts. They were choosing large systems in order to have economies of scale. But then there's been the industry thinking that if I make smaller reactors, 50 megawatts, 100 megawatts, I can, like, the name that is escaping me right now. There's several companies that are working on that, but they're looking at 6 packs or 12 packs. So I have several. So then the control system could be common, and you're looking at common control systems for multiple units. So that incremental cost is not, I have to make a control system just for each individual small reactor. I'm controlling several, so that doesn't increase my costs. I'm preventing the economics from going bad on it.
And that's essentially right. I mean, you're 100% right on the reason why they went for gigawatt and more than that was economies of scale. And so those aren't the reactors we're competing against. So we really identified a previously untapped market where nuclear, or in fact, nothing other than diesel has ever been able to touch, and that's remote location. So when you're looking at mining projects, remote habitations, island communities, military bases, disaster relief areas, anything like that, diesel generators have no competition. So even other renewable forms of energy, they can't be deployed anywhere you want because they do require some more optimal conditions. So you need good wind or you need good sun. So like if it's the Arctic and there's no wind, then it's diesel generators as an example. But if you shrink down and you create these microreactors and you mass produce them and to create that economy of scale, then suddenly nuclear can be deployed to areas it's never been to before. And the market is potentially infinite. So even it could be maritime vessels, charging stations for EV vehicles, AI data centers where you're removed from grid. And even we've had countries such as Indonesia and the Philippines, which have millions of people living on island communities that are run by diesel generators, looking to try and replace those with something cleaner, something smaller, like a microreactor that can then power their communities.
So for people who are unfamiliar with diesel reactors, when they're used at a military base, is one of the main problems is that logistics of getting in trucks and tankers full of diesel to power like a 2 megawatt system would mean I'd have to have a large tanker truck coming in every day, perhaps multiple times per day. In order to do that, in a military situation, that could be shot up and have a problem getting logistics in. That was a common problem in Iraq and Afghanistan. But for an island, you're constantly bringing that in. I don't have it sitting there in my gas station. I need to have that shipment coming in, which could be time-consuming and difficult and expensive.
Yeah, and on the military side, I mean, we've beginning to speak to the military, and they even have mandates where they have to have a certain amount of power for a certain amount of time without needing resupply. So I think, for instance, the Air Force have a mandate of 2 weeks, but that's 2 weeks of diesel fuel that they would need to stockpile. And then again, that's a target at that point as well. And speaking to the Army as well, even in places like Afghanistan, the logistics and the manpower required to ship in daily amounts of diesel to power the entire bases, and these things can be quite large, can really occupy an enormous number of personnel, and it can affect your ability to deploy troops for operations.
And the alternative of, oh, why don't we just use solar or wind? One, the conditions might be good for it, but two, in order to get a megawatt of solar, I must have a Costco roof and parking lot full of solar if I'm in a sunny location to do that. And then I don't have it at night, all that kind of problems. And if I was to say I'm going to use batteries to handle the night, I would then need to scale up by 5, 10, 20 times in order to have the extra power, which is many, many acres.
Agreed. So it's not that they haven't investigated this. What they did was they looked at the land requirement to produce that amount of energy, but then you need to sort of take that by 4 or 5 times to make up for the inconsistency. And then once you're producing surplus, you need to store it. And so you need like a big vanadium battery, and these storage systems can get quite expensive. So it becomes quite unfeasible quite quickly when you're looking at these different solutions to diesel. And so that's even happened to island communities too. They obviously examine these sort of things, and if you combine the land that's required, combined with the storage, combined with the inconsistency that you can expect, you do get these difficulties. And really, they've identified the microreactors are really the only solution around this, like a compact form of fuel where you don't need to refuel it for 10, 15 years. You have all of your fuel in one place.
So let's discuss the technology then. So you're saying you get massive size reduction by removing the need for complex cooling, large cooling systems, and then the reactor itself. What is you're using non-regular levels of uranium? What's the enrichment levels that you're looking at?
So it's very similar to, you'll probably see a lot of these new SMR and microreactor designs being put out by companies like Westinghouse or X Energy, but principally a lot of them use HALEU fuel. So HALEU fuel is fuel that's been enriched up to about 19.75%, below that 20% threshold that you're allowed. And that's permissible as a civil fuel. Anything above that would you begin to step into sort of proliferation and more weapons grade material. Even though the delta between HALEU and weapons grade is pretty enormous, but still that's where it's capped. And so within our reactors, you'll have a grade of enrichment throughout the reactor. So you'll go up to that 19.75%, but other parts of the reactor to flatten the power profile will be down at 5%, 6%, and you'll see the sort of a gradual enrichment through there. And that's something we're seeing pretty much a conclusion of most SMR and microreactor companies. They want that higher power density. They want to have less fuel essentially, but then you've got to go with that slightly more enriched fuel. A civil power reactor would use sort of 5%, somewhere around about there, 5% or less. But then you've got a huge amount of fuel that goes into that. And really, with these sort of things, you want a very small amount of fuel. And just to be upfront as well, even if you were to operate one of our reactors, because uranium is so power dense and you operate it for 15 years, the burnup would still be 1% or less over that entire length of time. That's really how compact this is, running at full power for that amount of time.
And what's the form factor? There's pebble bed, there's rods, there's also molten, but what kind of form factor are you using for your fuel?
So we want to just keep it simple. So it's just going to be conventional fuel rods. And there's certain advantages there. Like if you stick with conventional fuel forms like dioxide or nitride or hydride, there's a huge amount of database there, especially in raw. And when it comes to something like licensing and regulatory approval, something that the regulator is familiar with and can reference easily is going to cause you a lot fewer issues. Even with TRISO, the DOE spent billions of dollars qualifying certain type of TRISO, but then if you go and modify it at all, then you need to have almost a new regulatory process to approve that modified TRISO. And there aren't big data sets for it. So you could run into issues by using that more exotic type of fuel.
Yeah, so for people unfamiliar with nuclear industry, even Lightbridge, which it is specialized in making new kinds of nuclear fuel, if you change it's a rod, but they change it to look from the edge instead of like a solid circle, more like a an X or a T cross T in order to have more surface area on it to have heat dissipation. That has taken I think over 10 years. I wrote about my site. It's been 10 years. They're still doing certifications and tests. So by just making seemingly a trivial modification, it just adds many, many years to what you're doing.
Exactly right. And we've got to be conscious that we want to release a commercial product, and we want to release it not in 20 years, not in 15 years, not in 10 years. And so you've got to play ball with the systems that are in place, and that means that conventional fuel forms and conventional fuel types, there's big advantages there. And so going that direction allows us to one have a greater chance at a commercial product much sooner.
And then so the fuel rods are just regular. The amount of enrichment is again in going into the box of what's readily approvable. So then you have size limitations, or what are the other limitations in terms of in order to get down to the size without needing the cooling? What are the parameters that you're looking at?
I would say one of the big limitations of trying to contain it within an ISO container was the fact that you can't configure the core exactly as you would like to for say optimal performance, because it's got to fit within almost sort of a rectangular shape, and so you end up with almost a bathtub shaped reactor system. And obviously we found ways to combat that by reducing the size of the core and having two of them separated, and then heat exchangers and a system between them. And that's one way to combat getting around it. But obviously, if you think about heat dissipation, then you would almost want sort of a conventional sort of circular core type system where it can equally distribute heat. And so getting around that has obviously been some constraint. And even once you've generated that heat, converting it into electricity within that confined space can reduce sort of the efficiency of the conversion. So say, for instance, our reactor can produce 5 megawatt thermal. To convert that to electricity, because of the confines and the shape of the reactor and the placement of the turbines, that might not have a great efficiency, and you might be looking at 1 to 1.5 megawatt electric from that 5 megawatt thermal. So for industry, great, 5 megawatt thermal, you ship 4 or 5 of these things to remote locations, fantastic. They just want the process heat. When you're powering communities, you might need more of these things to come in, and they're modular systems, but they'll need to compensate for that that suboptimal conversion from thermal to electric, as an example.
So it's when you say a container, basically you're talking about the standard shipping container, which is the size that you see on all semi trucks that they're pulling one around. So that's the standard size, about 40 feet long, 8 feet tall, 6 feet wide is the standard shipping container. And the Tesla battery Megapack with 3.9 megawatt hours of battery is also the same size. So, but the difference with your 2 megawatts at that size is that it is constantly running for 15 years as opposed to just temporarily storing power and discharging power like in a battery pack.
Exactly right. And so, for instance, even on the topic of electric vehicles, one big limitation for electric vehicles can be, say, traveling across country, there might not be charging stations periodically placed. And for instance, if you do have a charging stations for those kind of vehicles, how are you going to power that power station to charge those vehicles in the middle of nowhere? And one solution can be microreactors actually for these vehicles. If you put a remote charging station for your vehicle somewhere in the middle of Arizona or Nevada, and it can sit there for 15 years, and so any truck that can come by can draw power from that, and then it continue. Really, it opens up the possibility to really electrify the entire transportation grid, and that's not really been possible for that charging station cannot be put anywhere you want. If you want to go with a renewable system that uses wind or solar and a big storage system, it then becomes a very elaborate operation rather than one small modular reactor that's ISO container size that can just be put there. And that's the big advantage there, is all of the fuel that you need for that entire life of operation is upfront and contained, and it does not need that refueling that, say, that truck would need on a very regular basis.
So the demand for the future of electricity, because we're going towards all electric cars and trucks, if you're replacing 25% of the 100 million barrels per day of oil for that purpose, you must increase the amount of electricity by about 25-30%. So from 4,000 terawatt hours up to 5,000, 6,000 terawatt hours in the United States, and then globally even more. So the electricity demand from electrification of transportation is huge. And now with the move to AI and AI data centers, the demand for electricity could end up being multiples of the electricity that we need now. And the issue of the grid, it takes years to make grid, decades to make grid. And that it goes to, I can put it where I need it faster if I can mass produce it.
Yes, and then we're seeing that even big companies like Microsoft now, they're appointing people specifically with it from the nuclear industry to try and source nuclear options for powering things like data centers and AI centers. And something like an AI center is going to be particularly energy intensive because it's not like it's a linear increase as it becomes a more sophisticated thing. Because of the interconnectedness of the network, it becomes a very exponential energy drain. And actually, the limitation with AI might not even be technological, it might be energy. How long can you sustain the power supply for something that energy intensive? And you can't just put that up to the grid and draw all that power. That grid is already there for a reason. It's supplying housing and industry and medical facilities and all of that. And so the tech companies are looking at remote locations and remote power sources. And up until now, really, the solution has been those diesel generators. They're consistent, but it's expensive and it needs a lot of logistical support, and it gets very expensive. Like, we were speaking to some remote communities up in northern Canada, for example, and they were telling us that a community of 800 people, they require about $10 million alone in fuel costs just for 800 people for a year. And that doesn't include logistics costs or anything like that, just raw fuel costs. And so it gives you an idea of how much this can cost. And a microreactor that can come in can pretty much, when they're mass manufactured, beat out the costs of these diesel generators and the costs of associated logistics to bring in this fuel. So you should see as we become a more technological civilization, and these data centers and AI centers are going up more, a lot more utilization of nuclear as a solution to this.
And you have agreement from Sam Altman of OpenAI and Elon Musk. Sam just had an interview with Lex Fridman for 2 hours, a second interview, where he said there will be unlimited demand for compute, and the limitation on compute will be energy. And then he did say nuclear fission and fusion would be his vision of the solution for that problem.
Yes, and he's even becoming invested in the nuclear world now, trying to navigate what he sees as he's anticipating big problems, essentially, because, I mean, obviously he's one of the spearheads behind the AI revolution. And, he can see where the problems are going to fall. And they're going to fall on the energy supply system. So even he's getting very heavily involved now in the microreactor space as a way to mitigate against these impediments that will hit it. And unless it does get resolved, eventually AI will reach a plateau where it's just not economic, it's not feasible, it can't be sustained, and it can't advance. And so, yeah, nuclear is going to have to be the solution. And the good part there is, obviously, there's infinite amount of nuclear fuel. It just needs to be made. It just needs to be mass manufactured. It needs to be done safely. And the new technologies and the advances in material science do permit us to concurrently develop those technology systems in combination with more advanced nuclear technology, smaller and more deployable.
Just as a brief aside on the aspect of nuclear fuel, roughly about 65, 70,000 tons of raw uranium are used every year for the roughly 350, 400 gigawatt of nuclear power that the world uses. And if we were to increase that to a large amount, there are 5 to 10 million tons at least of uranium in the mines right now. So that would last if you increase to 100,000 tons, 50 years, 100 years. And we haven't even searched on land for that much for the uranium because we didn't need to. And there's high enrichment deposits in Canada, probably coming from space. And there is 3.5 billion tons of uranium in the ocean, which would be constantly being replaced by erosion from land. So going to a high power uranium nuclear fission-based economy is something that would scale up 100 times. So let's discuss the scaling. You've discussed you have to go to factory mass production. So what will that look like in terms of mass producing these reactors? What would the cost and economics look like?
So, as you know, like even with the first pharmaceutical drug costs millions, and every subsequent one will cost pennies because the big capital costs will be the design, the demonstration, the licensing, and the manufacture of the first reactor. But even studies by University of Texas and the Idaho National Laboratories have shown that they become very economic even once you get to about 8, 10, 12 microreactors once you're producing them. The way that's probably going to be best done is that if these things are mass manufactured in a cheap manufacturing way, because they are so simple, you could 3D print these things on almost like a conveyor belt consistent system. They will need almost a different setup to a conventional civil power plant where you license the site and it undergoes its own separate site licensing process. But if you do have a mass manufacturing operation where you are mass 3D printing these things, the regulations around deploying these will likely need to focus more on reactor needs, when the area it deploys to needs to meet a certain number of criteria. So seismic conditions, temperature conditions, flooding risk. Provided it meets those conditions, it can deploy to that area. And that does allow for you to then mass manufacture these things and deploy them more quickly without individual site licensing processes for each individual reactor's deployment. And that strips down the cost enormously. And the nuclear can be expensive, but it's not expensive for the reasons people think. It's expensive because all your power is up front, and it's not like a diesel generator that is intermittently refueled throughout its life. But because you have that arrangement, you have the big upfront capital cost. But the biggest cost actually is financing related costs. So, like when you have a big upfront capital cost for a nuclear power station, 70% of all the costs will be financing costs related to that capital cost, and it becomes very expensive. Strip down that capital cost, the financing cost reduces. And so when you're mass manufacturing those, capital cost goes down even further and the financing related costs strip down even more. And then you start getting very cheap very quickly for these power units.
Two questions there. One would be the feasibility of the 3D printing of a complex system. There are the examples of rocket companies like, I think, Rocket Lab and some others. They're trying to make a complex product and mass produce them. So that's something similar to what your approach will be?
Yes, I would say that conventional power stations and reactors are probably too complicated for 3D printing because you need something that can almost build upwards. But as you take a conventional reactor and you strip it down to, say, SMR size, the complexity actually reduces quite significantly. And if you take an SMR and you shrink it down to microreactor size, the complexity goes down again. Far fewer mechanical components and working parts. And that does allow you to then create almost the entire system that can then be 3D printed at scale. And it probably, and far simpler than a rocket. Like we have some familiarity with rocket science. And those things are way more sophisticated than a microreactor would be. I mean, I don't want to simplify a reactor too much, but if uranium gets hot and it thermally conducts heat, and then you're just taking that heat off. You need very few pumps and mechanical components to be able to facilitate that. And at that point, you can 3D manufacture these things. And in terms of number, I mean, the market is fortunately potentially infinite. Feasibility to manufacture these things, because they're very simple, provided the fuel is there. There's no reason why you can't manufacture hundreds of these a year, quite easily. Really, on a day-to-day basis, you could feasibly produce maybe one of these a day, and then a team just to assemble them together, deliver them to site, fuel at site, and then they operate very simply with very few people needed at site to again allow for that scalability. If you were to say have someone for physical security and someone to be able to physically intervene like a mechanic at site, then that reduces it almost to 2 people for each microreactor, with a central hub location where all your engineers can monitor the transient behavior of the reactor through its operating life, and then intervene remotely as they need.
So you'd be getting up to about the level of the passenger airline industry, where Boeing and Airbus each make on the order of just shy of 1,000 major airplanes per year. So you'd be making possibly a few hundred, maybe up to 1,000 at that level, which would then be about, if you were to do 1,000, that'd be 2 gigawatts if you're doing the smaller systems. But in order to really handle more than the niche cases, if you wanted to get to some scale cases for the transportation system, then you would want to get to perhaps 100 gigawatts per year. So stepping up from, let's say, I don't know, 10 years, 20 years, whatever the number is that you get to that 1,000 units per year, a significant contribution to your major commercial success. But to step up to civilization impacting levels like the AI data energy needs, then you need to scale up another factor of 100 or 1,000. So how would that look like?
You're absolutely right. So microreactors will obviously cater to more remote locations where energy requirements aren't as substantial as sort of gigawatts and that sort of thing. But the good part here is that the actual SMR technology, so it's larger scale. So somewhere between 20 megawatts and 500 megawatts is really classified as a small modular reactor. But functionally, I think none of them are really going to be below 50 megawatts in terms of power, each one of them. And that technology is actually more advanced than the microreactor space. So the good part is they're not in competition with each other. We really want to see the SMR big players succeed, the TerraPowers, the X-Energies, the Kairoses. If they succeed, that actually makes the industry far more accommodating for microreactors, because it builds out that national infrastructure that we can then utilize for our own benefit. And you'll see a combination of things. I think the days of the big power plants, the gigawatt power plants, might not be as economic or as common once SMRs start deploying out, because they should be cheaper, they should be more modular and more manufacturable and quicker time to deploy. And microreactors even more so than that. And the combination of the two, it could make for a very robust infrastructure. It could reduce fossil fuel usage right across the board, from bunker fuel and maritime vessels to EV charging stations. And then, as you say, big grid power stations and replacement of power requirements for things like big infrastructure like transportation. Nuclear can do it all, and we know it can, but it's never been able to be done before. And because we were obviously going big and we were supplying big grid systems. And so this is going to be a different form of deployment.
If you're making 1,000 per year, or even 100 per year, what is the rough cost that you're estimating? Like the first of a kind cost, and then there's steady state production levels. Where do you see that number going? Is it?
So we know with microreactors, once we do start mass producing them, and the costs begin falling, after about 6 to 7 years of operation and mass manufacturing these things, the cost of a microreactor, actually the cost of the energy that we'll deploy will actually be below a diesel generator in these remote locations. So We
So what,
expect
30
to
cents
do a
per
lot.
kilowatt hour, 10 cents per kilowatt hour? What are we looking at there?
Well, I'm not actually allowed to say
Okay, I'm gonna say, okay, we know.
Yeah, but we know what it costs diesel generators in terms of bringing in that fuel and operating it. And we know that when the first reactors are produced, we will obviously be making a bit of a loss to be able to compete with them. But actually, we get underneath their costs within about 6 to 7 years. And within about 10 years, we're at a point where they are being manufactured to a level where there is no alternative and we can beat everybody on price on those kind of things. And so I think the good marker on price is that those remote diesel generator systems at mine sites, oil and gas sites, remote industry, habitation, we'll be able to beat the cost of that completely.
And then the so you're looking to get that level. So when do you think you'll be able to make your first reactor, assuming some funding happens?
So SMRs will likely to be deployed before microreactors, and we're pretty much joint in the lead with everybody else in the microreactor space at the moment. We're in the lead. How this is looking at the moment is we're going to start demonstration work this year, and that means physical test work. The reactors are through the concept level, they're designed out, and now we start the physical test work. And we expect 2 years of test work, nuclear and non-nuclear testing with rigs to build up the data set we need to then go to licensing. So in 2026, we'll start that process. And currently that's the NRC estimates about a 14-month process. So call that 4 years. That takes us out till 2030 in terms of when, and during that 4 years of licensing, we'll build our manufacturing facilities. So once that licensing process is complete, we'll have a commercial product ready to deploy in the manufacturing facilities capable of producing a lot of these things. And so the early 2030s is when we'll really see these things transforming the energy landscape.
And you're choosing, making all the choices where it's standard fuel, standard components, supply chain, thermal conversion, all ready to scale to thousands of units because it's very similar to existing infrastructure, just nuclear fuel, regular fossil fuel type energy conversion from heat to electricity, put into a form factor for a shipping container.
Exactly. You don't want to overcomplicate this. Obviously, if it's in a perfect lab kind of scenario, you can always design the optimal perfect reactor system, but it always falls apart once it hits the road. Go very simple, keep it very basic fuel forms, basic materials, basic technology, off-the-shelf stuff, and then you streamline the whole process for yourself later on. And so that's the approach we've gone for here. Nothing exotic, nothing the NRC, the regulator, hasn't seen before, and that should streamline our entire timeline all the way through to production, including even building out those manufacturing facilities. Even they should be relatively simple to be able to produce a lot of these things.
Okay, well, exciting times, and look forward to getting updates as they happen. So thank you. If anything else you need to discuss or...
No, that's great. Thank you very much for the time today, Brian. That was a very interesting interview.
Okay, thank you. So.